All right, good morning. Welcome to the session again. So before I continue on with this example problem that we're going to develop, just do the complete solution, write it as a system of equations, just to make sure that we're comfortable with getting things written as systems of equations. I just quickly maybe want to just highlight what I've uploaded or to click up, so make sure that everybody's on the same page. So I'm going to just switch to my sharing mode. So I'm just going to quickly share my desktop, and I'm going to go to Blackboard. All right, so what I just want to make everybody attent about is under learning content, there's essentially a lot of the things that we've developed so far that I've uploaded there. So I haven't put an announcement out for each one. I just want to make sure that everybody's, hopefully you'll get announcements, these daily announcements that there's been changes to the course that will announce that there's been updates. But so I've just uploaded essentially the beam formula derivations that we did, the displacement, distributed load derivation to get to displacements, and then essentially a lot of the stuff that you've developed on the board, I'm making now available as notes as well. So what I want to make sure is students that are struggling to access the videos at least have content that they can work from. So I'll try to upload the week's stuff that we develop on the board. I'll write over on a piece of paper, and I'll then essentially upload those versions to make sure everybody has access to that. So I've also uploaded the statically indeterminate beam example that asked about yesterday. Let me show you. So there's essentially, that was the request. So this example I've just essentially developed and uploaded the derivation for you. But also I've uploaded essentially a notebook that will, the Python implementation of that example for the statically indeterminate. So that will help you then hopefully also with the tutorial, getting comfortable with Python, etc. So I'll just show you that example briefly. So here's the example. And I just want to highlight one or two things before I continue on with the rest. So here's just an example of the derivation where we have the 4 unknowns that we want to try and solve. So we have to set up a sort of a small 4x4 system. The one thing I just want to make sure that everybody's comfortable with is once we use linsolve to solve something, what we get out essentially is what this thing returns. The solution is a SymPy sets.sets.finite set object, and that's a hairy object. That's quite a nasty object to work with. You can't really extract items out of it. You can't do anything nice with it. So the important thing to do is when you use linsolve is to take the solution that you have and first convert it to a list. So just take list brackets and then put that solution, that object in there. That will convert it to a list object, and then you can work with a list object, or if you want to, you can convert it then to a matrix object. If you directly try to convert this thing to a matrix object without converting it first to a list, it will give you a bug. So this is something that I just want to make sure everybody's comfortable with. The solution, linsolve, sends something back that is a hairy object, and we can't really work with it nicely. And so it's important we first convert it to a list, and then we can work with the list directly, or we can convert it to a matrix. Okay, so that's essentially that. And all I've done in this example is I've just essentially showed you how you could go about solving it when you want to solve it as a system of equations. And there's a second solution that I've just shown you how you want to solve, if you want to solve it not as a system of equations, but as a set of equations. So if writing it just as equations equal to 0, equal to 0, equal to 0, this last one, you can also use linsolve then to solve for the unknowns. Okay, so that's essentially just to make sure we're all comfortable with the two approaches we can follow. I'm going to hammer more or less in this course the system of equations. So, and the reason for that is just the whole point of the finite element method is to take a very difficult problem of continuous fields, as we'll see later in this week and next week, where we start with displacement fields, we have strain fields, stress fields, and it's all continuous fields that we have. The whole aim of finite element method is really to take those fields and to convert them into a set of linear equations. So that's essentially the whole aim of the course, is to take all of these continuous functions that are quite tricky to work with and to try and convert them to a place where we can work with them quite easily. So that is just to make sure I recap that quickly. Okay, so any questions before I proceed with this example, continue with this example problem? Yes?
Yes, excuse me, sir. You don't need to be sharing your video anymore. Just sharing the OBS application through the application share should be enough, and that should also help data rates to go down.
Right, so if I could take that off, is that good?
That should help with data, yes, sir. Yeah. And then also there's a question about the stream quality being low. Is it possible that you can tweak the OBS settings to just stream at a higher quality?
So I'm streaming at streaming at the highest quality that I can on this side. So I've got a 1080p camera. Just check here. So my resolution at the moment is 1080. So unfortunately, what you're seeing is as a result of Blackboard. So is it low for everybody? Can I just get a confirmation of that?
The camera quality is quite good, sir, but the previous when you showed the Python, it wasn't. It was very blurry, 144p like.
When I showed this, it was poor quality.
The Python, yes, sir.
Yeah. So is it poor quality as is?
We don't see it at the moment.
All right. Let me just make sure I show it. The quality now still low.
Yes, sir. It's visible, but it's very grainy.
Sure. Okay. There's unfortunately no ways I can check here. So that is again, that's supposed to display at 1080p. So the settings on my side. So if it's not 1080p, then all right. Let's see how we can. I'll see if I can do a test again to see if I can get the resolution of the desktop up. But there's nothing much I can do about it at this stage. It's supposed to show as 1080p. So I'm not 100% sure at the moment what is Blackboard doing. So what is resolution quality due to Blackboard and what is due to my own settings. But as far as I have it on my side, everything's supposed to stream full resolution to allow Blackboard to downscale as is required for each student in terms of the bandwidth. Okay, so let's see if we can get that sorted out at some point. As was it yesterday the same problem with the Jupyter, with the notebooks, with the Python? May I ask? Can anybody confirm? Was it yesterday the same issue? That the notebooks were much lower resolution than the video? No answer. Okay. All right, I'm not sure what to make of that then. Okay, but if you have a chance, or type the message and I'll
People are saying in the comments yesterday the notebooks were better.
Were better yesterday than today?
Yes. I can't remember.
Okay. All right, so let's see if we can, hopefully by tomorrow, everything will be smooth. Hopefully we're converging towards a solution that works for everybody. So it's a bit of a learning curve, so I do apologize for that not everything is going as smoothly as I hoped, but I promise you I'm trying my best. So let's see if we can get the things going smoothly. Okay. All right, so where were we yesterday? So essentially yesterday, we just started to talk about the derivation here in terms of this little example problem. So let me just first recap again where we were. So we had this clamped beam with a distributed load Q, and then we had this spring inside in here. And when we started looking at the number of equations and number of unknowns, we realized essentially, initially, if you look at only at the equilibrium equations, we only had 2 equilibrium equations. So we needed a third piece of information, which is what we derived to try and help us to solve this problem. Because essentially the unknowns in the problem were the reactions, the RA and the MAs here, so these reaction loads, but also the force in the spring. And the reason for that is the force in the spring was dependent on how much things deflected. So it was it's a strong function of the stiffness. So I went through this sort of example problem yesterday where I said, let's imagine the spring stiffness being close to 0. Then essentially it's as if that thing doesn't exist and this thing can deform freely. The other extreme is to say, let's imagine the spring stiffness to be essentially infinite. And then essentially this is like a roller constraint that we had. And it means this thing will essentially just behave quite differently. So that's in essence where we are. And so we needed to have a way to try and calculate what was the deflection of the spring. So initially the spring was undeformed in that state. Then what we said was essentially due to the loading Q, we have a displacement at L of VQ. And then due to this reaction force in the spring being there, it wants to push back. So there's essentially a displacement that is now VR at L that's pushing it back. And if I look at how much the VQ pushed it down and how much VR pushed it back, there's a delta S that remains. So that is just if I sum the two here, a delta S remains, and from that I can go and calculate the reaction load. So the magnitude of the reaction. This is just the equation to get the magnitude of the reactions out. Okay, so this is essentially what we have. This is now, again, if I write the formulas in a way where I say VQ is a large negative value, VR is a smaller positive value, and the sum of them would be then essentially some negative distance. And if I multiply the negative there, I get something positive distance out multiplied by Q, and then this R represents just the magnitude. Or we could have worked in a different way where we just wanted to have consistently down as positive, up as negative, and things would work out the same way. Okay, but that's essentially where we were. Let's see if we can quickly solve this. So what we just have to do now is to see what is this expression for VQ and what is this expression for VR. And so for that, we can now continue to develop that. So I'm going to just clean up a little bit the board so that essentially we write down the equations nicely. What are our sum of forces around 0, sum of moments around A, sum of forces in Y to be 0, sum of forces around A to be 0, and then this equation that we have here. And let's write down our system of equations. Okay, so first off, I think all of this is now stuff that we understand quite well. So I'm going to just wipe this off. So this was our linear superposition that we employed there. So let me just write this down that we have our first equation. Equation 1 was essentially R equals to K delta S, and that's what we write down as minus K VQ at L plus VR L. This is just to show that we now have a system that's solvable. Okay. So in order to solve this, what we have to do is to say, okay, well, let's look at the beam tables for what is the formula for VQ, and let's look at the beam tables, what is the formula for VR. Remember that VQ is our system that looks like this, and VR is essentially just a point load version. So for that, I'm going to just switch back to the PDF view. And so for the PDF view, so if you want to look at what's going on for the displacement at the tip, or the displacement formula as a function of x for this beam of length L, so let's just write this formula down here. We can afterwards plug in our value for x equals to L. So let's just write down that first. So that equation is V is equal to minus P x squared okay, so that is what we have for displacement of this one. So this is our formula for VR. And just take note that if we use this convention that downwards is positive, if this is a positive value, then the deflection due to this load would be downwards. So that's why there's the negative there. If I work with what is VQ's formula, which is the one that we derived, X. It's one that we derived way in the beginning. So that's the first one we encounter in the course. That's that formula there. Okay, so these are two formulas that we have. And so all that we have to do is let's evaluate both these. Both are now a function of x to make sure it's a function. Yes, does anybody want to say something? I'm still on the, this is it. I'm still on the, so all I've done is I've just written down over the formula for VR from the tables, and I've written over the formula for VQ from the beam tables. So here's this formula, and there's the other formula there. Okay, so all that we have to do is now is to evaluate each one, which is now a function of x, just at x equals to L. So for that, we can then say, just going to write this here and substitute these formulas in there. So that's just R is equal to minus K multiplied by minus Q L squared over 2EI multiplied by 6L squared minus 4L squared plus L squared. So that's essentially what we have there. And then I'm going to make sure that we add in the next one. So if I think of P as the magnitude that I want to solve for, so I'm going to use this, or if I want to make sure that the displacement that I get out essentially is a positive. So I'm just going to either take away the negative, or I can think of it as, because it's positive, the P should be negative, and the negative direction from which the beam tables work, because the notation was downwards is positive for Q, and then we have a negative displacement. But either way, I'm going to write it in a way that I get out a positive value here if P is positive, and then P is going to be implying this way to be positive. Okay. So there's that expression that I have. So what I have is a large negative quantity, because Q is going to be some positive value that I plug in here, and here I'm going to get some last positive, a smaller positive quantity out. And then that's why I multiply with the negative to make sure it's a positive delta X to get the magnitude for R out. Okay. Am I calling now P or R? Oh, so let me call it rather R. So I've called this reaction RC. Let me just make this R as well, and this R as well, because R is essentially the load that we have. That's the load that we get from the spring. Is that should be an R, and that should also be an R. Okay. Don't want to confuse. Start mixing up symbols R's and P's. Okay. The P is it's now got into my head from the beam tables. So this is the expression that we have. This is one expression that we have to code. So I can essentially see that there's an R here, and there's an R here. So I can go and rewrite it in a way that we can work with it. So let's start with that. So now I can take off this and write down the equations. Let me just save this one for now, because this is all utility functions that we use to get us to this point. So let's write it, and we can just group things a little bit if you want.
So someone made a correction to the equation in the chat.
All right, what is the issue?
It says it's QL squared divided by 24 times EI, not QL squared divided by 2EI.
Ah, thank you for that. 24. I thought I'd written the 4. Okay, didn't. Thank you for that. Yeah, EI. Is it at least legible? Or is it large enough that everyone can read it? Seems that's good. Okay.
Yes, sir.
All right. So thank you for that. So all I'm going to do is I'm going to move this term across to this side and group it so I can pull out R. Just going to write it a bit neater. So that's essentially if I pull out the R, I'll get a 1. Then if I take this term, it gets multiplied by a negative. So I take it, so it's a negative term, but I take it across, it becomes a positive. So that is essentially the R I'm going to pull out. So that's K gets multiplied by that L squared 6EI times 2L. And that gets multiplied by R. And that is then essentially equals to everything here is known. K, Q, L, there's no unknown in here. So I can leave it on this side of the equation. The negative multiplied by then will become a positive then. K, Q, L squared 24EI. And then I can say, if you want to simplify it, this is essentially 7 L squared minus 4L squared. So that is essentially what happens is 3L squared left. Okay, so that is what we have for that expression. So I can just wipe this off. And then we can write out the other two equations that we need. So let me know, shout if there's a sign issue, if I forget to add a K here or multiply something out. I think I should have gotten most of it. Okay. Then what we have is we have sum of forces in the y direction. And again, let's just write down our free body diagram for this example. So this is long gone. Should have cleaned this a long time ago. So our free body diagram looks as follows. So that's what we have. So let's look at sum of forces in the y direction should be equal to 0. So what I have is essentially FA. So I'm going to work now with being just the normal up being a positive, down negative, just because that's sort of the standards we've always been used since first years. So essentially the force load applied by this distributed load is Q times its length. It's a QL. So that's negative QL. And then plus R should be equal to 0. So that's one other equation. And then sum of moments around A should also be 0. So if you think about this as the positive, MA, the weight is considered to be the positive, as with our notation. So MA, FA has no moment arm, then Q times L times L over 2, so it's a uniform load, so the force acts in the middle, so that will be then also in the positive direction for this Q. So that's essentially plus QL times L over 2 for the arm. And then R will be in the negative direction, so that's negative R times its moment arm, which is L. And here's my equation. So this is equation 1, equation 2, and equation 3 that I need to solve for. And again, I can write it nice and compactly in a system of equations, and that's where I would like to get to now. To make sure is this bottom there. Just can everybody see this bottom? Yeah.
Yes, sir.
Yes, sir, we can.
Thank you. Thank you for that. All right, so I'm going to just write it quite wide, so give me myself some space. So I'll write FA as the first column, MA for the second column, and R for the last column. And then the right-hand sides will be whatever they need to be. Okay. So if you look at the first equation, there's essentially no MAs or FAs in here. Is that clear? So FA and MA 0. We have this term that multiplies with our R, multiplied by that thing. So that is going to be 1 plus K L squared over 6 EI times 2L. That is what that term is. For the second equation, let's also write the right-hand side before I can forget that. So the right-hand side is just this term here. So I've already written it nice and conveniently in that form. And you can simplify it more if you want to. I'm just writing it to get it down. And then essentially, this next equation is F minus QL plus R is equal to 0. So F's coefficient is 1. There's no moment. And then what R's coefficient is again 1. This must go towards this right-hand side, so that becomes QL for the right-hand side. And then the last equation is this. And for this last one, there's no F. So the coefficient for F is 0. M's coefficient is 1. Second column. R's coefficient is minus L. And then I can take that toward that side, and that becomes minus QL squared over 2. And there's a system of equations that I can solve. So two of them are equilibrium equations, and one of them is what we call the compatibility equation, or making sure that we recover the force in the spring from the displacements due to the Q load, as well as the load in the spring that's pushing back. Any questions up to this point? All right. Does anybody want me to start solving this quickly in Python, just to get the ball rolling? I'm not going to solve the whole thing in Python because that's really what I want you to do in the homework or the tutorial. But is there anybody that would prefer that I just quickly get going on how to start solving this? Or can I move on to the next part of the course?
Could you get started on showing how it's done?
I'll do that. All right, so let me open up my desktop again. Where am I now? In the wrong part in the course. Let's get to week 2. New Python. So I'm going to just call this beam spring. So example. Let's be careful what type of symbols you put in here. We can save the file names. Beam spring. All right. So that's, and I'll just say it's. Okay, so there's essentially what you have. All right, so what we first have to start looking at is we can solve it in one of two modes that I explained before. The one mode is where we set up this matrix, coefficient matrix. We set up this right-hand side, and then we solve for the unknowns without having to define the unknowns. So I'll start with that version. The other one is obviously where we just set up the equations with the unknowns in there, and then we can solve those equations by specifying which equations you want to solve for using those 3 equations. So let me start off with setting up this matrix version, and I'll just make sure I highlight a couple of possible tricks, or not tricks, things that could cost time if you're not careful. So import SymPy as SP as usual. And then I'm going to ask myself, what are the variables that are present here? So there's a K, there's a L, there's a E, there's a I. Is there anything I've missed? So symbols, and just take note, symbols is lowercase. The reason I'm hammering this is because later when I'm going to define the matrix, it's going to be uppercase for the matrix. If you use a lowercase for the matrix, it's going to give you a bug. So the function for the matrix is uppercase. Okay, so that's what we have there. And now I can just start by saying, let's start defining this coefficient matrix. So I'm going to start off by saying SP dot big capital matrix. And then I'm just going to specify a list of lists where this first list is going to be the first row, this coefficient. And then I'm going to have a second list, which will be the second row. And then a third list, which will be the last row. So this will then encapsulate the last row. So when you specify these matrices in Python, always row by row. So 0, 0, and then I have 1 plus k times L times squared divided by 6e times I. Again, be careful not to do this, just to write EI. That's typically how I would write it down on pen and paper. Let's remember to multiply. That's something that you have to multiply out times the 2L. So that is the coefficient, that's this coefficient here. And I can say, let's look at this second row, which is just 1, 0, 1. Last row is 0, 1 minus L. Okay, so let me just do that, and then I can print for you. So there's the matrix that we've defined. Okay. And then I can do the same to find the right-hand side, and then I can use linsolve to solve it. And then I can start playing and ask myself, verify whether I've made a mistake, whether I trust what I've done. And that is going to be sort of what I want you to focus on in the tutorial. The doing part, as you've seen here, is really seconds. Setting this up on SymPy and then solving it is seconds. It's really seconds to a few minutes. So what I want you to spend time on is playing with it. Ask yourself critically, what happens if I make L long? What happens if I make K stiff? Do I recover what I expect to see? Or is there something honky going on so that maybe I've made a mistake, a sign issue somewhere, and can I pick up that I've made a mistake? And that is really what the big part of this course is about, is not to always say that we're always going to be solving in a perfect mode, but it's to say, if I solve something and I have now an answer in front of me, do I trust that solution? And I'm going to hammer this point again, and the reason for that in this course is, if you think about what a finite element package is, a finite element package is a thing that supplies solutions. So you define the problem, you set up the problem, you apply the loadings, boundary conditions, and you clap your fingers, you press a button, boom, solve. What you're confronted with is a solution. What you as an engineer have to decide is do I trust that solution? And that's why I'm driving this course in that mode. Just want to make sure that you're with me on why it's so important that once you've got an answer, that's when the problem really starts, is to say to yourself, do I trust the solution? And again, we can do the sanity checks. What happens if you make K very, very, very low stiffness, or essentially near zero stiffness? Do I recover the solution of a beam with only a Q loading with no spring there? Or if I make K very stiff, do I recover the solution of a roller on that edge where the spring is? And that's the kind of stuff I want you to be able to do and play with in these tutorials so that you can get comfortable with it. Okay, so although the tutorial, the way it's set up, is just for you to get to the place of the solution, just to make sure I get you to get comfortable with Python, I do encourage you to please go and play with it to make sure that you ask yourself these critical questions. Do you trust the answer? Did you make a mistake somewhere? And if you've done it, can you figure out that you've done it for one, and can you then figure out where you've made the mistake? And I think that is very important in this course. Okay, so that is essentially that. I'm going to show one last thing in, I've been talking on the, all right, I've been talking on the, in front of the light board, but I've been, okay, doesn't matter. I hope everybody's at least heard sort of what I've ranted here, but that's really important. One last thing I just want to show you is, again, how quickly we can, if I have a matrix like that, define a specific problem. For instance, if I want to say my length is equals to 2 meters and my K is 1,000, if I want to start putting numbers into this thing, And I can very quickly do that by substituting. And the only things that are remain are the E and I, which I haven't specified. So we can use this dictionary where I specify the variable or the symbol, double dot the value. Or it doesn't have to be value. It can also be something else. It can be something. This is just for illustrative purposes, what I'm going to show now. So it's not sensible what I'm doing here, but I just want to show you, or let's maybe add another symbol. It's not going to be too crazy. Start doing too many functions. I'm going to add in a symbol B. So, oh, L is 4B. I can also, if I want to, substitute things like that. So this expression here doesn't have to be purely numerical. It can also be another symbol, for instance. So this is important because, again, what we solve is we solve first the generic problem. And then after we've solved the generic problem, get the generic solution out, then we can start looking at specific cases. So, oh, a length is this, or the stiffness is that, and now we start playing. This is why it's so important that we solve the generic problem first. But also, more importantly, just to drive the point home, so let me get back to the light board. Well, we'll get to the, but just to drive the point home again is solving essentially the generic case is what we're going to have to do in the finite element method. The finite element method is not a different program for each problem. It's not like when you solve cantilever beams, you run one FEM program. And if I solve trusses, I run another FEM program. Or if I solve sort of this type of structure, I run different FEM programs. You run one finite element program and it solves whatever it needs to solve. So this way of setting up, first solving the generic problem symbolically, not only serves the purpose that you really get good insight, because if you start ask yourself critically what's going on, how things scale with L, how things scale with K, how does things scale with E and I, you can get some insights into the physics, but more importantly also, parallel importance is also the fact that you can then essentially, you solve the generic problem, and then afterwards you run a couple of cases. Now you have a playground in which you can play, you can plug in your different values, and you can check whether you trust them or not. And you build up essentially that way, you build up confidence and you build up insight into your problem. Okay. And again, I'm highlighting the fact that finite element program will give you, one program will give you solutions to many different problems if you plug in different values. So this is also just to sensitize you towards where we're going to go when we develop the finite element material for this course. Okay. All right. So this essentially concludes this example problem. And this sort of concludes the, I'd say sort of what I call the sort of background knowledge of the course, just to get everybody up to speed, to get the MOW227 students comfortable with statically determinate and statically indeterminate problems, making sure everybody's sort of in a good place. Okay, so that is really what the aim of this part of the course was, is to make sure there's not a big difference now if you had MSY310 or whether you had MOW227, although MSY310 students would have had a lot more practice at this. Hopefully everybody's conceptually on the same place. And now we're going to start walking into a bit more new territory as we go on for the remainder of this week, as well as next week. We're going to start first looking at displacement fields, get comfortable with that, get comfortable with the idea of geometries, and that we are approximating these things. Okay, so for that, I'm going to go back to the concept cards. So you'll see those concept cards that I've uploaded onto ClickUp. I'm going to just open up them and just space ourselves through a couple of questions there. Okay, so let me see if I've got it open. Sure, just open it first. Should open with Adobe. All right, so can everybody see that?
Yes, we can see it.
All right. And before I continue on with this, I just want to also just be clear that if you want to have additional examples and additional information, you're welcome to, for the MOW227 students, you're welcome to go to your Shigley book to look at what you've done there. Also, I can highly recommend the MSY310 book that Gear and Goodnow book. So that's also another good book to look at. And they cover all of this beam theory, the theory they'll derive in a different style to what I've done it, but they will go through exactly the same material and talk about linear superposition to solve statically indeterminate problems, or linear superposition to solve complex loading cases, so that you can leverage the beam deflection tables to a large extent to help you to be agile in terms of the design and verification. Okay, so that's just as a reminder. you're welcome to open up those textbooks. And I do encourage you, if you feel uncomfortable with what we've done so far, please open up those textbooks and have a look. Okay, but I just wanted to make sure that you understand the concepts are quite lean, and they are very, very much understandable, and it's easy to get comfortable with them. Okay, all right. So again, we've covered this. So this is now what we've concluded for this week in the course so far, is talking about statically determinate and versus statically indeterminate. So when you start looking at these graphs, you'll have now much better feeling why the left-hand side is statically determinate and why the right-hand side is statically indeterminate. But more importantly, you actually have now sort of the appetite to actually solve these problems now as well. You've been equipped now to solve each of these problems with quite ease. And as you see, by leveraging Python, we really get rid of all the nitty-gritty algebra and really on the conceptual side. Okay. I want to just start taking us further in terms of what is the solution to a structural mechanics problem. So if you start looking at structures around us, if you look at that sort of tractor building here, what we see is there was some severe deformations there. Here's some example of actually a finite element. This characterization of some building, you'll see some triangles there. So you'll see essentially that surface triangulation on that structure there. So that's the method that we're going to be looking at. And those triangles that you see there is the methodology that we're going to use. Because if you look at the example of the train below, you can see it's quite a complex field that we're looking at there. That's the pressure on a train, on a high-speed bullet train. So that is a scalar field. So at every point in X, Y, and Z, there's this value for, there's a value for pressure. And that's a scalar field. But you can see the variation is quite complex. And to have a generic expression in terms of x1 or x squared or y squared and z to the power of some polynomial or some description for a polynomial over this whole train, it's going to be way too complicated. So what I'll show you as you go into this course is we're going to, instead of trying to solve this complex field in one go, with one function, we're essentially going to be breaking this up into small little triangles. And then each triangle is going to be a very simple field that we have to describe, because if you just look at the little small patch there, the variation is quite trivial. And the variation around a small patch there is also quite trivial. And there as well, it's not that hectic. So then we have small little polynomial approximations. So that's really what the finite element method is, where we're going to driving about. Okay. But again, if you look at this, again, I want to sensitize you towards a design point of view. Sometimes what is important is the displacements of a structure. So sometimes that's the issue. Or the strength of the structure, something. In other cases, the issue. So here's to show you if the strength failed, then you get severe displacements. Here's an example of some hectic ice train in Germany with lots of impacts and lots of stuff going on there in terms of fracture and damage to the train, etc. So that's really what it boils down to. What I want to make sure is that I hit home is what we are going to be focusing on in terms of the solution to structural mechanics problem is the displacement field. Okay. All right, so essentially, when we solve a structural mechanics problem, we want to be able to find functions that describe how each point in the structure displaces in 3D. So that's the displacement field. So if I know every point in the structure how it displaces, hopefully from what we've done now in terms of the beams and the bar kind of examples, is that you're comfortable that if you have the displacement field of the structure, you can go work backwards to find out what is sort of the slopes or the moments and the shear forces, or as we'll see, what is the strains and the stresses in the structure. So if I know what the displacement, the deformation is from where the body was and how it's deformed, I know essentially everything about the problem if I include the material and the geometry over which it acts as additional information. Okay, so that's essentially the main part. From that displacement fields, they are related essentially to strains, and we'll do derivation of three-dimensional strains. We just get comfortable with where that comes from. But again, I want to make sure that you understand the difference between a displacement and a strain. A displacement is where how a point moves, irrespective of its neighbor. It doesn't care what its neighbor is, it's just how that point moved specifically. And strain is essentially what was essentially the relative movement between 2 points that are closer to each other on the structure. And that is something that's related to the stress. Because again, if I just move a book in space up and down, or if I move my mouse cursor, my hand on the mouse cursor left and right, you can see that hand. That hand is not stretching, it's not becoming bigger or smaller, it's just translating. And there's essentially zero stress and strain involved when I think of it from a quasi-static point of view. It happens slowly enough that there's no inertial forces on that thing. But if that hand, if I were to do something to that hand to make it wider or to make it higher, then I'll be starting to stretching that thing. Okay, so it's really the same of blowing a balloon up. It takes pressure, but just moving it in space without blowing it up, just moving left and right doesn't require any pressure. So that's essentially another way you can think for yourself. But that's just to make sure that we sensitize ourselves between the difference between displacement and strain. And then again, the strain, we can, if you know something about the material, then we can essentially get an idea of how the stresses would look. Okay. So the types of functions that we're dealing with are essentially going to be vector valued functions. But before I do the vector value function, I first just want to give you an idea of just, again, a scalar function. I've already spoken about the version of the pressure. So pressure is an example of a scalar function inherently. So at every point, there's a single value that defines what is the pressure at a point. Temperature is another cool example of scalar function. If I just have essentially a point in space, it's got a temperature. So that's a single value that tells you what the temperature is at a point. Okay. Sometimes we can have quantities that are derived from vector quantities to give us scalar quantities. Here's an example of that. So this is essentially a material that if you put stress, if you strain the material essentially based on the strain that it sees, so it's really strain related. So the strain it sees, it gives you different colors in the polariscope, and those color bands can be related then essentially back to what is the strain that the thing is experiencing. This protractor, for instance. But again, what we're seeing here is not the strain in its full glory. We're seeing a scalar version of it. So that's essentially a different color at each point. So that's essentially a scalarized version. It's almost like taking a stress that you have as something that has X and Y and shear components, and you convert it to a von Mises kind of quantity. So von Mises, which is you scalarize essentially stress to get some of the important information out. That's another way we can get scalar functions. So I hope everybody's quite comfortable, but bear in mind, if I move my hand around different X and Y points here, I will get a different value. So to describe this function, I need to be able to describe as a function of X and of Y, what is the value? And in this case, the redder, the higher, the bluer, the lower. So that color bar is low and small, so you can't really see there. Okay, so vector functions are essentially just multiple scalar functions. So if I'm at a point, it's not just a single scalar that tells me what's going on, it's maybe two or three. If it's a two-dimensional vector function, there'll be two scalars that tell me what's going on, and together they'll be sort of forming a vector. If I have a three-dimensional point, there'll be three values that will tell me what's going on at a point. So in this case, in a 2D example, this point can displace in Y. So that's that little delta that you see there, and it can displace in X. So that black dot is where it started, the red dot is where it ended. There's the black dot where it started, there's the red dot. So in this case, things only displaced in Y, but it could have displaced in X. It has that freedom. So the X component here was a 0, and here you can see as we go more and more towards the left, essentially the X component starts to, as I go away from the center line, the X component starts to go away further more and more. And what it essentially boils down to is that we have a certain description for this problem, a certain coordinate system, in which you describe this sort of in regionally undeformed case towards this deformed case. And there is essentially the vector mapping that's taking any point here to a point where it's now on this deformed, so that BH is now there, this is there, that is there, and that is there. Okay, so that is essentially what a vector value function is. It's just multiple scalars, multiple values at a point, and they are usually also related through some underlying physics. Okay, so not just arbitrarily. But this is an example of uniaxial tension, how the displacement field would look. So it might not be always as simple. It also depends on how I choose my coordinate system to describe that. This field might look more and more complex or less complex depending on how I make my choices. Okay, but this tells me then something about how the structure deformed and displaced. Okay, so what I want to just highlight now is in terms of, I'm talking about we're going to be approximating functions. And you've done that before. So all of you have done quite a lot of function approximation before. In MKM321, often you had some data. When you had Excel, for instance, or Python, I can't recall which version you did it, but you had some data maybe in Excel, and you had to fit sort of a line through the data. That is essentially, once you've got the formula for that line, you have then approximated the data with that line. So you've regressed some information, some function through some information. And the MPR way of approximating functions is really what machine learning is all about, or AI in today's modern world, is to say you have lots and lots of data, and what our people are doing is they're doing lots of effort to regress very complex functions through those data. And in the end, you walk away with a function. You can throw away the data, and you can then ask questions with that function. So I could essentially, if after I fitted this line through this data, I can also ask, what is the value there? What's the value there? What's the value there? But also these dots, red dots, could have been lots of large amount of data. It could have been terabytes of data, like 2 or 3 hard drives full of data. But afterwards, when I walk away with that black line, it's something I can write in pen and paper, or it's something that's a few kilobytes in size. So it's essentially, it's a way to not only build models, it's a way to compress. There's so many analogies you can think about what's going on. But in essence, what we are interested in is to try and get an approximation for that black line, to that function, and then that essentially then tells us how things are displacing or moving in this structure. So here's an example of the vertical displacement of a beam. Okay, but for this to work, you need lots of data. Okay, so for this to work, you have to have already observed the beam deforming. So you have to maybe build the beam and then deform it. And in MKM, the scenario is a little bit different. What we are typically start off with is we have sort of the boundary conditions of the beam, we have the geometry, we have the material with which it's made, maybe the loading that we've applied, and that's it. And now you're asking me, how does the thing deform? So if I leverage this idea of regression, essentially what I know about this problem is, in terms of vertical displacement, is the displacement there is 0. That's the vertical displacement there. I have no idea how to relate the force to the displacement of the beam if I don't do some physics. Okay, if I just think of it now from a data point of view, that's not something that's useful. So I can't just do the MPR route directly to say, let's regress with very sparse data and say, let's fit a line through this. It's not going to be useful exercise. Infinite number of lines will go through this. Okay, plus, how do I relate this F into this kind of regression problem? This F is additional information I'm throwing away at the moment because I don't know how to relate it, and how it's related is via physics. So essentially, when we come to a sparse information problem, as opposed to an information problem with lots of information, the only thing that we can do is to invoke some understanding of the problem, physics, and that's essentially what Newton has been doing. Galileo, Newton, Leibniz, Cauchy, all of those great names in history of mathematics and history of developing physics. Essentially, what they did is to try and understand with very limited information, how do I build sort of functions that tell me what's going on? If I just supply that little bit of information with understanding of the problem and with writing down some closed form solutions, we can then fill up the rest, so that we actually essentially can end up with only limited information, tell you what is that black line, saying what is the displacement anywhere, or what is the strain anywhere, what is the stress anywhere. That is really the aim of this course. So I just want to make sure I contrast it clearly to everybody that it's highly related to machine learning and AI and data science. It's just on the one extreme where we have the least amount of information available. Where if you were a data scientist or machine learning expert, AI expert, you would typically have lots of data, and then you just regress some complex shape through that. So that's just to make sure that we're all on the same page there. Okay. And so essentially what we are doing is the additional information, like I've said, is really coming from physics and structural mechanics theory. Okay. And then that allows us to help us to solve the problems. And to also relate information that might seemingly upfront look unrelated, to relate them into a sensible way with each other. Because additional information that we have is the force, we have the material that is made, and the geometry that we all want to be able to leverage. Okay. Again, this is just to that aspect that I've driven home in the past a little bit, talking about the reality, linear elastic theory, and finite element approximations. So we are now essentially, theory is telling us simplification of the real world, regression is approximating that theory. We have to have an understanding of what do we expect the displacement fields, strain fields, stretch fields look like in each of these worlds, and how they differ, and which differences are legit, and which differences are because of mistakes. That is really important. Okay, I'm going to conclude with this slide just to make sure that you understand all of this cool stuff that you see nowadays with the GANs that we've spoken, I think, previously about when I spoke about the study guide. I can't recall if we went through this or not, but the bottom line is when you look at these people, none of them have ever existed on this planet, and that's really just a model that was built on lots of data. So that was a purely regression problem, the one that you did in MPR213. The only difference is the model that was, the function that was fitted through that data was highly complex, and the data was lots and lots of terabytes. But in the end, you can then evaluate that model to get faces or get people that didn't exist at all. We are going to be on the other extreme of the spectrum to say, how do I generate this face? Yeah, without having all the data. That's essentially the equivalent of what we're going to be trying to do in this course. Okay. So I think I'm unfortunately out of time, but I'll continue tomorrow with this slide to talk about essentially the comparison between structural mechanics and continuum mechanics, just to make sure that we can relate to what we've seen a little bit in the sort of beam formulations of the problems and where we're going to go in terms of this pointwise field problem where we have these vector fields for displacements and vector fields for strain and vector fields for stress that we want to try and essentially solve for. Okay, so maybe I should not talk only about vector fields. We're going to talk about tensor fields for stress and strain because they're going to be sort of these matrices at a point, not just 3 values, or they can be sort of 9 values of which 6 are independent, for instance. But that's stuff that we'll get to then tomorrow. Okay, any questions up to this point? Has everything been fairly clear? Can I get an idea? Is everybody on the ball? If there's any questions, please pop me some. I'll try to read the messages afterwards, and then we can move on with that. Okay, thank you for that. I'll see you tomorrow. These slides are already on ClickUp, so I just want to make sure that everybody's with me. These slides are already onto ClickUp, so they're already they're called the concept cards to be continuously updated over the semester. So the slides that I've just shown you now are in those concept cards. That's giving us the structure of the first couple of weeks of this course, and I'll add some more concept cards progressing the course. So that's just to give you an idea of where we're going. So those concept cards are already on ClickUp. Please take note. All right. Thank you, everybody. I'm also going to leave, and then we'll chat tomorrow again. Thank you. Goodbye.